So welcome back to this new series on battery modeling in pybamm. So what's lined up next in this series? This video will cover the first one, which will be on battery database available within pybamm. We'll check what are the different chemistries and cells available as a predefined database to easily plug and play and pick the database values which are derived from some literature. And then we'll see how we can update some of the parameter sets values and compare the results. In the upcoming videos in this series, we'll cover the remaining topics, which includes type of models, including DFN, SPM, SPME, which are single particle model, and ECM, equivalent circuit model. And following that, we'll be covering performance calibration, which includes OCV and performance, which will include higher C rates and even temperature effects. And then following performance calibration, we'll jump on to aging calibration, which will cover aspects of calendar aging and cycle aging and different aging mechanisms available within pybamm. And then lastly, once we complete the calibration process through rigorous optimization techniques, we'll also be exploring some of the optimization techniques available in pybamm and see what's the right way to calibrate a cell, including global optimization and fine-tuning. And then lastly, once the cell is calibrated, we'll look at real-world aging prediction over a drive cycle or a daily commute pattern. So this will be the agenda of the series. Let's jump on to the first one, which is battery database and parameter update. So firstly, if you're starting from scratch, then you can either use any of the Python IDEs. I'm using Visual Studio because it provides different autocomplete options and also comes with an agent. Alternatively, you can also work with Google Colab or any other Python compiler that you feel comfortable with. So to begin with, we have to install pybamm. So we can start with pip install pybamm. If you haven't done so, please do that. I have already installed, as you can see here. Next, we can import pybamm, and then we can start off with trying to extract what are the available cells within pybamm. So for that, let's print out a list of pybamm.ParameterValues. So what this code will do basically is extract all the available cell options and list it down in a list format. Okay, so there we go. We have a list of all the cells available. So it's hard to identify what the chemistry of these cells would be, right? Just by looking at the name. Although some of them have names like graphite half cell or graphite silicon half cell, which are easier to identify. But the other ones like Chen 2020, we don't know unless we have read the paper. We don't know what the chemistry of this cell would be. So as a next step, let's try to identify what is the underlying chemistry and the parameter values used for this particular database cell. And also moving forward, we will be comparing, we'll be also updating the values of the base parameters. So let us start off by creating a variable called base param, and then we'll assign a value. The good thing about Visual Studio, code is that it also provides autocomplete. So it makes your job easier and you don't have to remember all the syntax. But it will come with practice. So if you're new, maybe the autocomplete might not be very accurate, but over time it will improve. So let's consider base parameter, and we'll set it to pybamm.ParameterValues, and then we'll select the Chen 2020 cell. Yeah, and also let's print the base param value. So when we do this, it basically extracts the parameter values of this cell database and then list down all the values. So it's a long list, and you can use the scrollable element to see the complete list. So you can see in this list, you will have options like the current function, which will be the default current. If you don't provide any instructions for current, it will pick up 5 ampere. Then it consists of height, width, inner dimensions, conductivity, diffusivity, some electrolyte parameters, followed by some negative electrode and negative particle parameters, followed by some of the voltage related aspects, capacity, and then positive electrode parameters. It also consists of thickness of different layers like separator thickness, and also negative electrode thickness and so on. So these are some of the parameters which are tuning factors as we calibrate the cell and as we proceed in the series. But for the time being, let's understand how the parameter update process works in general. So we have created a base parameter which will store all these values listed here and assign it to this variable so that we can call this later when we want to run the simulation with a given set of parameters. And the reason we are storing the base parameter is because in the next steps we'll also update some of these parameters. So just to keep a track of and have the base parameter stored somewhere, we have created this variable here. So let's now move on to the next step, and let's create a copy of this, and we'll call it param. And what we will do is use the function base param.copy. So this basically will create a copy of the base parameter variable, and it still has the same values. So now we can use the function param.update. Param.update followed by opening of small brackets, and then within the brackets we need to provide, so the syntax is as followed. Within the curly brackets we need to provide the variable name along with the variable value. So let's open the curly brackets, and then we will pick up one of the parameters. Let's pick diffusivity for the negative electrode, a negative particle. So negative particle diffusivity, we'll just copy along with the units. And for the timing, I'll also copy the value here. So this is how we update the parameter. Although I've not updated the value yet, but for the sake of comparison, let's first go to the next steps and then see how we proceed with the results. And ideally, since I have not changed the parameter, upon comparison of the voltage response, it should overlap with the base parameter values. I'll keep it as is for now and then move on to the next step. So so far we have created or we have basically copied parameter from Chen 2020 library and saw how we can update the parameter. We'll come back to this shortly. Next step is to define experiment. So now what we want to do once we have updated the parameter, we would like to see how the cell discharges over a 1C current until the cell reaches the lower cutoff voltage. In this case, the can identify the lower voltage cutoff, which is 2.5. Will discharge until 2.5 at 1C. So that's our experiment. And the way we can define this in pybamm is very straightforward. We just need to define a variable experiment and then start defining the experiment. So the syntax is as follows. And it's best to indent it properly for ease of reading. For example, this is how you would set it up for a cycle, which means you have you would like to charge the cell at 1C until 4.2, and all these are kind of predefined keywords within pybamm. So it understands plain English while defining experiments, and it is able to derive all the quantities it needs. For example, when we are charging, we are doing a 1C charge and we are stopping at 4.2 volt, and then we hold at 4.2, which is the CV mode, until C by 20. So this is the cutoff current. And then finally we discharge at 1C until we reach the lower cutoff, which is 2.5 volt. So see, we have defined it in plain English and it will still be able to understand. For the time being, let's remove the other two statements, and I'll just keep the discharge statement to keep it simple. So have the statement discharge at 1C until 2.5 volts. Next, I need to define the next up I need to define the model which I'll be using for this study. So the model used in this study would be SPME. So pybamm.lithium-ion.spme, which is the single particle, and E should be small. It's the single particle model with electrolyte. And now we will be creating solutions, but before that, let's understand how the setup works. So we are basically trying to run two separate simulations, one with the base parameter, the other one with the updated parameter, and then finally we'll compare the voltage curve. So for that, we'll have to create an array of solutions. Let's call it sols, and what we'll iterate through is the parameter set. So for P in params, and we should also add params array. So this is the base param and the updated param array which we have defined, and the same array we are using here. So for P in params, which is basically base param and param, it will iterate through these two one by one. What we want is to run the simulation. Sim equals to pybamm.simulation, and use the model. So the syntax is model, comma, experiment equals to the variable which is used to define the experiment, which has the same name here, fortunately, but it could be a different string as well. And finally, the parameter values, which will be iterated through this variable P. So this is the syntax to create a simulation, and then we'll use sim.solve to solve it, and then finally store it in solution. So this sol is basically what we will finally append to the list. So once we have the sim.solve set up, we should also provide an initial SOC, because the initial SOC could be different than what we intend to use. It's mentioned here, but in case the initial SOC is different, to be safe, let's provide it explicitly. Initial underscore SOC equals to 1. Since we are discharging, we'll start with fully charged cell and then discharge till 2.5 volts. And then finally, we'll append this solution to the sols array, which was empty initialized earlier, and we'll end up getting 2 sols in this array. So once this is done, we can simply run it. Okay, we got our first error. It says for p in params. Since we didn't run this, probably it came out. Yeah. So since params was not defined, was rather defined later after we ran this, gave this error, and now it works fine. So with this, we are ready with the solution with base parameter as well as the updated parameter set. Now lastly, let's plot the result, which is the voltage curve. We'll import matplotlib.pyplot as plt. Then let's define t1 equals to sols 0. So sols 0 will pick up the first solution, which was base parameter in this loop, and then 0 is the index, so we're picking up the first one, and then from there we're picking up the time result and all the entries. Now it might be hard to identify what these exact strings would be available in the solution. We don't know what the solution contains, right? Like there could be time, voltage, current, etc. So to find that out, you can simply use this small piece of code. It basically is printing in a list format. So it's picking, let's say, the SPME model, which we have defined here, dot underscore variables dot keys. And when we do this, we get a list of all the outputs we can extract. So for our plotting purpose, we need time, which we have defined here. And also we would require voltage. So let us see the syntax for voltage. So yeah, there we go. We have terminal voltage here. It was a long list. I briefly paused the video to find it out. There are also other ways to find with the strings, which we'll cover later. But for now, this is the string we are looking for, terminal voltage V. So let's copy this and we'll store it as V1 equals to sols 0 terminal voltage dot entries. Next, similarly, we would like to have T2 from the second solution set and V2 from the second solution set as well. And then finally, we'll plot plt.plot T1 comma V1, and then let's give a label as base. Similarly, we'll do T2 V2 label updated diffusivity, or we can call it the updated dataset. And then finally, we'll define the XY labels and add legend. So X label is time, Y label is voltage, we'll add legend, and then finally make the plot visible. So with this, as we run the code, we can see that base and updated diffusivity overlap, which was intended behavior since we didn't modify the diffusivity value in the param dataset. So now we can just adjust this by changing it by, let's say, 2 orders, and we know that diffusivity affects the knee region of the voltage curve, which is which makes it go in either directions as we increase or decrease the value. So we'll see a deviation in the voltage. That's what we expect. And now let's rerun the code. We can also use this run all the code below this, which will allow us to run all at once. When we click this, it will run through all these steps. It's currently here, running the 2 experiments. And then finally, we have the results. So we can see that the base parameter had a voltage curve which had a knee bending down earlier as compared to the updated diffusivity, which aligns well with our initial understanding. So this is how you can extract the values from the database and also update the values using the param.update options available within pybamm. So far we have just updated one, but the best practice would be to also list it down in a nicely indented way, so that you just need to add a new parameter set here. Let's say we can also pick up the diffusivity from the positive electrode. So positive particle diffusivity, let's pick this up and append it to this list. Let's change it by 1 order, and then again let's run everything below this, and now we can see the curve has further updated. So this is how easily you can update the parameter sets. You can either derive them from literature or do an optimization study, which we'll cover in the next videos. Finally, I'll leave you with one nice piece of code. So far, it was kind of a manual way to extract all these parameters, find out what are the cell database options, and then identify from the list whether it's a NMC or a LFP. So if you look at some of the inputs like OCP, it has the name predefined, but it's not a guarantee. So this name convention can help us identify what chemistry is being used, and this is what I've extracted with a piece of code which I'll add in the description. And this is the one which basically has a for loop which iterates through all the names in the parameter set list, and then it iterates through each of the cell, extracts the chemistry, positive electrode OCP, negative electrode OCP name. This will help us identify the chemistry. So chemistry here is just lithium ion, but we also would like to know the anode and cathode type. So this OCP string might help us identify that. And it also extracts the cell capacity, lower and upper cutoff voltage, which are kind of the most important ones to begin with. So as I run this code, you will see the output in the form of nicely formatted data frame created using Python, and it's easy to read from this one. So we have all these 17 cells available currently in pybamm. These are the chemistries. Most of them are lithium ion, some are ECM models as well. This is the equivalent circuit model, which we'll cover later. Then there's one for sodium ion, one for lead acid. And we can see the cathode options, which has NMC majority, one is LFP, and then some more chemistry combinations. Anode is again dominated by graphite, but has some mixed options like hard carbon and some silicon based composition. Then we have the capacity values and min and max voltage. So I hope this video was helpful. I'll leave this code in the description. And then thanks for your time. See you in the next one.